I am Somesh, working in the University of Malta, and I will present a bit of the multi-agent frameworks of scheduling fully electrified public transport. This problem is generally solved with the help of optimization. This is not a very this is just an alternate way of scheduling transport, but this is just an attempt. This is a disclaimer I wanted to make before I make the further discussion with this. So as we said, generally when we schedule public transport, let's say as part of planning, we see that it's a very non-Pareto hard, non-linear optimization problem, which involves several heuristics: charging, discharging, the schedule of buses, the types of buses, and the cost of operation of buses. These are several heuristics that are taken into account, and then if we involve the price, electricity, and the other market juggleries, then the problem just keeps becoming more and more non-linear. The variables are increased. So in this one, we solve this problem more as a post facto solution rather than a planning solution. So we would consider this as a real-time simulation-based mechanism rather than a planning mechanism. So we consider the public transport of the Maltese Islands for our studies, not the entire public transport map, but just a few of them. So how is the time-space evolution of the bus evolves? How the time-space evolves? So when a bus starts its operation in the morning, they deadhead from their depots onto the starting stations, and then they follow a timetable trip to the terminating stations. This is true for all the buses, and then they deadhead back to their depots. But when we have an electric bus, we can have another sort of additional trip that's a deadheading trip. By the way, deadheading trip is something which doesn't have any passengers. They are just running without passengers, and they are just performing other tasks such as maintenance, and in case of electric buses, they would be charging and parking and other stuff, I guess. Yeah. So with the multi-agent solutions, we have three kinds of agents. The bus agent, which is basically responsible for, they have the timetable, and then they have their own current location. The bus IDs are nothing but the bus numbers, and then what is the state of charge that they have at that point, and where are they exactly? Are they deadheading, or that will come on to later? What is the state of operation and the operating cost of the bus? So then we have the depot agent. Depot is the place where the buses are parked. Only in this scenario, we consider only a depot only for parking as well as for charging. And then the manager agent, which just overlooks the entire operation, and the other attributes are what are the timetables, what should be the route start time and the end time. So for the manager agent, the responsibility is that it should broadcast the next trip information for the bus timetable to the bus agents, and then the bus agent will give the operating cost to the manager agent, and then to realize the particular trip, it will calculate the minimum cost, the manager agent, and then it will dispatch the buses that yes, you can now start your trip. For the bus agent will receive the message from the manager agent, and then it will check if the time for the starting station is right as per the scheduled trip, and then it will see the feasibility of the range. If it is within the SOC range, that it can complete the n number of trips that it has in succession, and then it can calculate the operating cost. Operating cost, by the way, here is the deadhead cost for the trip cost and the trip cost summation. And then we check if the trips can be realized with the current available range. And then they communicate with the depot agents just in case if they need parking space or the charging space. And that's when the depot agent comes into picture, when if there's parking and charging space needed, they will provide the same information to the bus agents. To summarize these agent-based activities, so we have a number of bus agents, depot agents, and then the sitting on the top one sitting on the top is the manager agent. And the agent tasks are summarized that we have the route timetable and the minimum cost dispatch with the manager agent. The bus agent has the time feasibility and range feasibility, that can it do this trip or not within these specified state of charge range, and then it will calculate the trip operation cost. If it is all within range, it doesn't talk to the manager agent, and if yes, it talks first to the depot agent, and the depot agent will provide them a parking space, and this happens recursively. This is the public transport network that we considered, all from Valletta. We have other starting points too. One is the hospital, which we call it as Matthias. One is Valletta. These are the two major starting points for buses. Valletta is not considered as the depot in our case. We have considered 4 depots, and they are located all around the island. So for the bus data, we have 2 kinds of buses with us. They are basically based on the makes of the buses. So we have one bus which has 170 kilometer range on a single charge, and the other which has 120 kilometer range on a single charge. Everything is converted into kilometer per minute. Even the state of charge, the cost and everything is converted here in terms of kilometers here. So if we see the results, we see one case where we assume startup cost for buses, that yes, if there is a startup cost involved for the buses, then in that case, the first step would be that the buses will have to first see that what is the charge available, and they have the first responsibility to see that they have to finish 100% charge in order to start a trip. This is case 1. So with this, we see that we have kept a maximum capacity of type 1 buses at 40 buses, and then we kept T2 buses, the type 2 buses, as a variable. So we see that with case 1, for the entire day of operation, for the number of buses, we need 74 buses to fulfill all the trips needed. Similarly, for case 2, we keep a 0 startup cost, but we consider the state of charge as the superannuating variable. So unless the state of charge reaches, they will be provided the nearest depot in this case. So in this case, what is happening is that T2 buses have reduced, but since it is being provided the nearest depot, the operating cost has increased because it is having more deadheadings to cover in this case. Case 3 and case 4 are the ones with 80%, the upper cap of the state of charge kept as 80%. And now, since it has been kept at 80%, we see that the costs have increased because the deadheadings have also increased, both when we consider a startup cost or if we consider a state of charge restriction. So to conclude, we see that we have two types of buses with two operational costs, and we see that if we have less restrictions on the startup cost and the state of charge, then we require less number of buses, and we can also see that a multi-agent approach can be an alternative way to schedule public transport. Thank you.